How are you all? Today in this session, we are starting first law of thermodynamics, and hopefully by this lecture, we'll be completing how first law of thermodynamics. Then after that, we'll go for second law of thermodynamics. Before I proceed further, let me know if everything is all right, so that we can start the session. Can you hear me properly? Should we start? Okay. So let's start with first law of thermodynamics. First law of thermodynamics, it is simply the principle of conservation of energy applied to the system. So the statement will also be like that. Energy cannot be created or destroyed. It can only be transformed from one form to another, or it can be transferred between, say, a system and its surrounding. Total energy of an isolated system remains constant. So you can say this is the crux of this first law of thermodynamics. Now let's say how this works. Let's talk about this. But my pen is not working. Just a moment, guys. Okay, now it is working. So you see, as I've told you, energy can neither be created nor be destroyed. So if you provide some amount of heat, let's say dq, this is an infinitesimal amount of heat. This is used to do some work, and other portion of that heat is used to change the internal energy of the system. So let's say if you have a system here, okay, if you are providing some amount of heat, so it will neither be created or nor destroyed. So this will be utilized in two ways. One part will be utilized in doing the work done. Another part, what it will do, it will increase the internal energy of the system. So as you can see, no part is lost. You can, if you take the sum of du and dw, you get back your dq. dq is equals to du plus dw. So this is a mathematical form of first law of thermodynamics. You can note it down if you want. Now you must have known or learned about two things. One is path system, path function, and another one is state function. Do you know the difference between, let's say, path function and state function? Path function, let's say if you have some initial point and if you have a final point, so it's an initial configuration of the thermodynamic system, and you can say this is the final configuration. Now if the quantity value of the quantity depends on the path through which it is taken from an initial point to final point, that is the path function. So path function actually depends on path, depends on the path through which it is calculated. On the other hand, if you talk about the state function depends only on the initial and final point. Can you give me some example of let's say path function? Any example you know for path function? Good morning, Harry, Murli. Tell me, give me some example of path function. Any example you know of path function? Like conservative and dissipative? No, a function which depends on the path itself. The heat exchange is a path function. If you take a let's say thermodynamical system from one place to other, one configuration to other configuration, it will depend on which path you have taken that. Heat exchange is a path function. Work done is a path function. So obviously, if you have let's say a point here, another point here, so if you go straight, the work done will be something, and and if you go along this path, let's say, obviously here the path length is increased, so the work done will be different. So it depends on the path. Now, state function, can you give me an example of state function? State function, it may be internal energy. So let's say you have some system at some temperature. Okay, internal energy depends on the temperature, right? It is a direct function of temperature. So you have a system at some temperature. Now you have undergone various processes and make it to some other temperature. The internal energy will only depend on the initial and final point. It will not depend by which process you have reached to the other temperature, isn't it? The internal energy and entropy. Yes, Harry. Entropy. Now let's say here in the first law of thermodynamics we have got two things. One is, as you can see, it is internal energy and this is work done. So as you can see here, dq, this is a path function, du, this is state function, and dw, this is a path function again. So you can just get it. So a summation of a path function and a state function will be a path function. Now here we have something called work done. Work done in an adiabatic process is a state function. in adiabatic process, okay, yes, if you specify the ultimate formula, you get P2 B2 minus P1 B1. So in that sense, you can say it. But work done is generally considered to be a path function. But under a certain condition, it can behave like a state function. So let's say we have a PV diagram. So any point on this PV diagram will be denoted by specifying the value of P and V. Let's say if you want to take, let's say here it may be P1, here it may be V1, P1, here it is. Now you have taken this process, let's say this point is A. So from A, you are going to a point, let's say. So here also it will have some value of, let's say, the pressure and some value of the volume, let's say naming it P2. So you have taken the process along this path. You have taken your thermodynamic system along this path. Then work done in doing so will be the area under this curve. Okay, area under this curve. So work done when a process is occurred between A and B is W is equals to integration of A to B times P dV. Why it is so? You see, it is considered in this way. You can imagine it. Let's say we are considering an infinitesimal area like this. So for this infinitesimal area, you see the change in V is this dV. Change in V is like dV, and you can see the pressure value does not appreciably change. So P times dV. So this is an infinitesimal work done you have. Now if you integrate such infinitesimal element from point A to B, you will get the total work done. Okay. So in the PV diagram, look, this is valid only in the PV diagram. If you have a TS diagram, you will not say that the area under the curve is the work done. Only if you have PV diagram, then the area under the curve will be the work done. In the PV diagram, the area under the curve represents work done. Look, Anumita, you told now work done in an adiabatic process is a state function. So this is not actually correct. If you closely look at, it should be a path function. The adiabatic process, the way you carried out, that will decide the work done. Okay, we cannot say it directly from the formula. So what is the significance of the first law of thermodynamics? What does it give you? Firstly, you can see, if you look at this mathematical form of first law of thermodynamics, dq is equals to du plus dw. When you are able to write these quantities as a sum, we can say that these quantities are equivalent. So Q is a form of energy, internal this du is energy, that is quite obvious. So dw and dq, they will also have the unit of energy. So dq and dw, it's like a similar quantity there, that is why you could able to add them. The heat is recognized as a form of energy. This is the first significance in the first law of thermodynamics. Understood this very simple thing from the homogeneity of dimension analysis technique. Number two, energy is conserved within a thermodynamic system, meaning it cannot be created or destroyed. That is what dq has two parts, du and dw, and both you can see. You take the sum, you will get back your dq. Third, a thermodynamic system in equilibrium possesses internal energy, which depends solely on the state of the system. This law establishes the relationship between the heat and other forms of energy. It implies that work cannot be done without corresponding expenditure of energy in another form. So this is the significance of the first law of thermodynamics. Now, here while discussing the first law of thermodynamics, understanding sign convention is very, very important. What happened to my throat? Okay. Sign convention. This is very crucial, guys. There are two things in the sign convention. One is related to heat transfer. Another is related to work done. Now let's say if you have a system, if heat is entering into the system, what will be dq? And another case may be if heat is leaving the system, then what is the sign of q? So when heat is absorbed by the system, q is positive, and when heat leaves the system, then q is negative. Heat absorbed by the system, q is positive. Heat given off by the system, q is negative. Now what about the work done? Work done by the system. Work done by the system is what? Positive or negative? Tell me. Work done by the system, is it positive or negative? Ajay, Murli, Animita. Where is Joel today? Joel? Work done by the system. It is positive. Work done on the system, it is negative. Okay, let us take some different thermodynamical processes and we will try to implement the first law of thermodynamics. Okay. By the system positive, on the system negative. Yes, Harry. So remember that will be very much useful. Now we will consider different thermodynamic process, like firstly we will consider isochoric process. Iso means same, equal. Choric means related to volume. Isochoric volume, so as per the name suggestion, isochoric means equal volume. So when volume remains constant during the process. This is a signed convention, Murli. This is the signed convention. If your system is doing work, then you will take the work done to be positive, and when the work is done on the system, it will be negative. In chemistry, they use just the opposite. Okay, in physics we follow this. In chemistry, they use opposite, but for physics you have to use this. When volume remains constant during the process, that process is known as isochoric. So if we represent it graphically, how it looks like. So you are representing pressure and volume curve. If volume remains constant, if you have, let's say, a process here, if you have the initial thermodynamic state here, you are taking it to another point B. So equal volume means it will remain here. It is like this. Volume does not change during this process. So if volume does not change, so we can say dV is equals to 0. And as a result, work done dW, which is P times dV, this is also 0, and du, dq is equals to du plus dw. So du is equals to dq minus dw. So this is equals to how much? Dq, because dw is 0. So dq is equals to n CV. You can understand what is CV. CV is the specific heat at constant volume. So you can take away this formula, du is equals to n CV dt. This is a very important formula, du is equals to n CV dt. This is for the isochoric process. Let's go for the next process, that is isobaric process. Iso means equal, baric means related to pressure. Isobaric means when the pressure of the system remains constant. When the pressure of the system remains constant. Sorry guys, winter has come and this thing will start in the morning. And the pressure of the system remains constant during the process. So let's try to understand it first in the form of a graph, then we'll go for the mathematical explanation for this. So we have this PV diagram. It is constant pressure. So obviously this let's say we have a point here A, and you are going from one point to other. So if keeping the pressure constant, so it will be looking like this. And as you can see, pressure is remaining constant, but the volume is changing. N is the number of moles. So for this you can see there is no change in pressure, so pressure is remaining constant. So we can write work done, you know the formula, area under the curve. So integration of P times TV, this is the formula of work done. So P times, let's say if I consider this volume is V1 here, for this point B the volume is V2, so we can just write it P times volume at B, that is V2, minus volume at A, that is V1, and P is constant, so it is treated as constant. So you know the formula, PV is equals to nRT. You can write nR times P2 minus P1, because we know from the ideal gas equation PV is equals to nRT. Okay. Now from the first law of thermodynamics, what you can write from the first law of thermodynamics, we can write dq is equals to du plus dw, right? dq is equals to du plus dw. So dw we have already got. So what you can write? Okay, so w is equals to nr delta T. Now du we have already got n Cv dt, and dw is equals to nr, let's say dt. So, this is equals to, if you take n common, PV plus R. Now, you know, Cp minus PV, Cp minus PV is equals to how much? Equals to R for 1 mole. For 1 mole, Cp minus Cv is equals to R. So, Cv plus R is equals to Cp. So, N P. Remember this formula, dq is equals to NCP. So, we have got two formulae. One is du is equals to NCV dt and dq is equals to NCP dt. CP denotes specific heat at constant pressure. So, this was the second process, isobaric process. Let us go for the third process, that is isothermal process. Iso equal thermal means related to temperature. So, let us talk about the third process, that is isothermal process. What will remain constant here in isothermal process? Temperature. Absolute temperature T remains constant during the process. Okay, so if you look at it graphically, what kind of graph it will generate? You know, it follows what kind of graph it is? Yes, temperature. So, let us say you have a process starting from here, let us say at point A. You are carrying out this process via this path to this point B. So, along this process, the temperature is constant. This kind of graph you get. Which law is it? A temperature is constant. P is proportional to 1 by V when temperature is constant. What law is it? It is. Do you know from where it is? It follows. You see, from the ideal gas equation also we can say it is follow. PV is equals to nRT. N is a constant, R is a constant. If you make T is also constant, so PV is equals to constant. So here the equation of the process is, here this PV, the product should remain constant. This is a mathematical form. Boyle's law, yes. That is what I wanted to hear. What is the change in internal energy here? In the isothermal process, since there is no change in temperature, the internal energy change will be 0. In the isothermal process, since dt is equals to 0, the internal energy is also 0. 0 for ideal gas. Yeah. Till now, whatever thing we'll be discussing, it will be by default ideal gas. Then we'll go for the real gases. Van der Waals equations will be used. So, from first law of thermodynamics, what you can write? From the first law of thermodynamics, we know this very famous dq is equals to du plus dw. So, here we need to calculate the work done in an isothermal process. So, as you can see, if I project this line on the v axis, project this point on the v axis, this will give you the value of v1 and v2. This value is v1, this value is v2. So, dq, therefore, we can say this du is equals to 0 plus dw. So, this is what is dw? dw will be this area under this curve, isn't it? Which is p dv. So, from here you can calculate p integration of, you can calculate q integration of p dv. It is taken from point A to B. Now, PV is equals to nRT. Okay, P is equals to, you can just put the value. P is what? nRT by V times dV. Now, the put the limit of V at A, V is V1, at B, V is V2. nRT is constant, nRT, dV by V is ln V, V1 to V2. ln V2 minus ln V1. So, this is nRT ln V2 by ln V2 minus ln V1 is nRT ln V2 minus. And this is also the work done in isothermal process. So, we can write work done in isothermal process is given by this formula nRT ln V2 by, and you can also write it in terms of the pressure also. Look, during this thermodynamic process, press PV is constant. So, if you consider the pressure value at this point is, let us say it is a P1 and this is V1, and here the corresponding things are P2, V2. I should write the other ways because you first write the x coordinate then y coordinate, right? I write it in that way. Let us say V1, P1, V2, P2. So, P1, V1 is equals to P2, V2. That means V2 upon V1 is equals to P1 upon. So, this expression W isothermal can also be written as nRT ln P1 by P2. Okay. So, I am not writing it because you should remember only one. The other you can derive. If you try to remember both, then you will get confused. I will recommend you to remember this one only. W isothermal is equals to nRT ln V2 by V1. V2 is the final temperature, final volume, V1 is the initial volume. Let us go for the fourth process, that is adiabatic process. So, what happens in an adiabatic process? There is no heat exchange. If there is no heat exchange in this process, then dq will be equals to 0. And what about the equation? It is PV to the power gamma is equals to constant. This is the equation which is followed in the adiabatic process. PV to the power gamma is equals to constant. What is gamma here? What is gamma? Anyone? It is like we are revising class 11 thermodynamics. What is gamma here? Critical exponent. Mathematically, gamma, it is the ratio of Cp by Cv. Cp by Cv. Cp and Cv, what are those things we have already mentioned? It is the ratio of these two specific heat capacities. Now, this PV to the power gamma has some alternate forms as well. If you do not want to keep this P, you can just replace it by TV to the power gamma minus 1 equals to constant. You can easily understand P is equals to PV is equals to NRT formula I will use. Okay. So PV is equals to nRT. I am just deriving one of those. So P is equals to nRT by P. So we have PV to the power gamma is equals to constant. So P is equals to nRT by V and V to the power gamma, that is constant. Now n, r and all is absorbed at this constant. So you are left with T V to the power gamma and this minus 1. In this way you get this second form. Similarly, if you if you replace V by nRT by P, you will get P to the power 1 minus gamma e to the power gamma is equals to constant. You don't need to remember all of this. You just remember the first one and you can derive it simply using these tricks. So all of these processes, all of these equations represent adiabatic processes. Now for this process, here we have dq is equals to 0. There is no heat exchange. So dq is equals to 0. So PV to the power gamma is equals to constant. So let's say that constant we are taking K. So what will be the value of P? P is sometimes looking like rho, but it is P. K by V to the power gamma. Now dq is equals to du plus dw. This is from the first law. In this first law of thermodynamics, if I put dq is equals to 0, you have du is equals to dw if you talk about the magnitude. So what is dw? dw is equals to P times dv. This is the formula we know. So P is equals to K by V to the power gamma times T. And as a result, we can write the work done formula as K integration. Now let's say we need to express this process graphically as well. In the PV diagram, if you express this adiabatic process, the slope of, okay, let's say I'm just drawing it with the dotted line. Previously, let's say this was the process for the isothermal process. Adiabatic process will just be a little steeper. It will be steeper. So I have drawn this just for comparison. This is, let's say, A, this is B. This represents an adiabatic process. Just for comparison, still doesn't matter. Adiabatic, and this is related to isothermal. So here the volume is V1, here the volume is V2. V1 to V2, we have done adiabatic expansion. V to the power minus gamma dV. V to the power minus gamma plus 1 divided by 1 minus gamma. I better write minus gamma plus 1. Let's put the limit from V1 to V2. So you are getting it k times V2 to the power 1 minus gamma, you can write 1 minus gamma minus V1 to the power 1 minus gamma. We don't prefer to write the negative sign first. Okay. Now again, if we apply this formula of initial formula, you see P is equals to k by V to the power gamma. So what you can write? V to the power minus gamma. V to the power minus gamma is P2. So P2 into V2 minus P1 into V1. You see, this is actually k to the power V minus gamma. So k into V2 to the power minus gamma is equals to P2, and 1 V2 will remain, minus is V1 divided by 1 minus. So this is the formula of work done in adiabatic process. 1 upon 1 minus gamma times P2 V2 minus P1, and since PV is equals to nRT, you can also express it in this way: nR into T2 minus P1 divided by 1 minus. So using this formula, you can also calculate the change in internal energy. You see, dq is equals to du plus dw. So dq is 0. So du is nothing but the negative of dW. Here dW is not as like infinitesimal, so you can say the total work done. It is just the negative of the work done. But you will remember this one only. This is useful. This is just a derivation from whatever we have obtained. Everybody understood everything? Now, as I told you, as I have shown you here in this figure, slope of adiabatic is looking slightly steeper as compared to the slope of isothermal. Slope, you know, m value. So this thing we can mathematically prove also, slopes of adiabatic and isothermal process. The graphs, the curve in the adiabatic process is known as the adiabats. Adiabats. And the curve in the isothermal process is known as isotherms. Adiabats are steeper than the isotherms. So in a same graph, if you represent both the process, so let's say this is isotherm, the adiabatic will be steeper. You see, for an isotherm, what we have, PV is equals to constant. So this gives you P times dV. If you take the derivative on both sides, V dP, this is equals to 0. Why I try to give rectangle on. Okay, so what is the slope? If you talk about the mathematical formula for slope, it is dy by dx. If you consider y-x curve, right, y versus x. So here also dp upon dv, this represents the slope of this PV diagram, of this PV curve. So dp by dv is how much here? It is minus p by, just note it down. Now if I calculate the same for an adiabat, we have PV to the power gamma is equals to constant. If we take derivative on both sides, it gives you P gamma V to the power gamma minus 1 times dV plus V gamma into dP. This is equals to 0. So from here you get the value of dP by dV is equals to minus, if we P gamma V to the power gamma minus 1 divided by V to the power gamma. So you get minus gamma times P by P. Now since gamma is greater than 1, Cp by Cv value, it depends on the ratio of Cp and Cv, and it is greater than 1. We can say the slope of adiabatic is greater than the slope of isotherm, that is adiabats are steeper than the isotherm. इतने टाइम में तो लिख लेता मैं. अंडरस्टूड. प्रॉब्लम आ गया, बट यहाँ पे एक और चीज हम लोग को करना है. Okay, there is one thing left, but I don't have sufficient space here, so I am just making space here for another topic, that is free expansion. Let's say inside an enclosure you have some gas. This is an enclosure and this is a rigid enclosure. Heat cannot escape from it, or heat cannot enter into this. So it is surrounded by some rigid wall which will prevent the heat exchange. Let's say now we have some gas. Okay, we have gas. Now if we allow free expansion, so for free expansion what will happen? You are not doing any work. You are just removing this partition, let's say, somehow. And what will happen? This gas will expand freely. This is the free expansion process, and as we have surrounded it with some rigid surrounding, which what I should say, which prevents the heat flow or heat exchange, we can process this, we can consider this process to be adiabatic as well. No? In free expansion, there is no work done and the process is adiabatic. So mathematically, what does it mean? dW is equals to 0 and adiabatic dQ is equals to 0. So what will be du? du is equals to dQ minus dW, so that is also be. So there will be no change in internal energy in a free expansion process. That means the internal energy remains constant. We can add a line here that the initial and final internal energies of the system will remain constant. I am just giving a star and here writing. Okay, if you have a space, you can add it. The initial and final internal energies of the system is constant. So this is pretty much about the theory. Let's go for some problem. We'll look at this problem as shown in the figure. An ideal gas is confined to a chamber A of an isolated container with vacuum in chamber B. This is isolated, means no heat can exchange, no heat can come out to the surrounding. When the plug in the wall separating the chambers A and B is removed, the gas fills both the chambers. Which one of the following statements is true? Tell me quickly. Harry, Murli, Anumita, Ajay, tell me the answer. Very simple. A. Very good. Temperature of the gas remains unchanged. So this is the case of free expansion, right? Because it is isolated. So when you separate the plug, the gas is expanding against the vacuum. So this is a free expansion. So for free expansion, you know, there is no change in, there is no heat exchange, the zero, because it is isolated, insulated container. There is no work done. So du is equals to 0. Now you know du is equals to n cv dt. This is equals to 0. So dt is equals to 0. The temperature of the gas remains unchanged. चलो आगे बढ़ते हैं. Yes, Harry. Option A. Option. Okay, let's focus on this second problem. When an ideal monoatomic gas is expanded adiabatically from an initial volume V0 to 3 V0, its temperature changes from T0 to T, then the ratio of T by T0. Do it quickly, guys. You know this formula, if H equals to 3n minus k, n is the number of atom, k is the number of constraints. So Constraint means some given equation which is hindering the process, you can say. So, for monoatomic there is no constraints. If you consider the diatomic, so you see the separation between these two is a constant. So, if you consider rigid bonding, so for diatomic, T into number of atoms is 2 here minus K number of constant is 1. This is 5. And for triatomic, if you consider triatomic, what will be the number of constants? Look, this distance is fixed, one equation, this distance is fixed, another equation, this distance is fixed, another equation. Total number of atoms is 3 minus 3. So, how much? 6. So, if you consider the monoatomic, it is for gamma for mono atomic, it will be 1 plus 2 by 3. So, that is 5 by 3. Option B you are getting? Yes, option B will come. Let us go for the solution. So, PV to the power gamma is equals to constant, that you know, this is an adiabatic process. So, PV to the power gamma is, we have got 5 by 3, this is equals to constant. If it had given you diatomic, then you would have used this formula 1 plus 2 by 5, so 7 by 5 it would have been. So, P is equals to, for 1 mole if you consider, it is RT by V, V to the power 5 by 3 is equals to constant, or you could easily implement that formula, okay, if you could remember, or I will not recommend you to remember, you can derive the way I have just derived. We have basically used TB to the power gamma minus 1, gamma is equals to 5 by 3, 5 by 3 minus 1 is 2 by 3. So, instead of doing that, we have just derived it by putting P is equals to RT by V from the ideal gas equation. So, TB to the power 2 by 3 is constant. So, you can see the volume has changed from V naught to 3 V naught. So, we can just write T1 V1 to the power 2 by 3 is equals to T2 V2 to the power 2 by 3. So, you see you had V0 and you have made it 3V0, and you had T0, you have made it T. So, T1 is T0, V1 is V0, T2 is T, V2 is 3 V0 2 by 3. So, hence T is equals to, you can say V0 by 3 V0 to the power 2 by 3 times T naught. It's spelled as it is pronounced yet. Okay, is read at T naught, not G0. What has asked? The ratio of T by T, simple. V naught is getting cancelled, 1 by 3 to the power 2 by 3. Clear, guys? Option B also has been received by Ajay. Very good, Ajay. Let's go for another problem. Look, from thermodynamics, if you have understood few things, then it is very easy to solve question from thermodynamics. No such issue. A box separated by a movable wall has two compartments filled by a monoatomic gas of Cp by Cv is equals to gamma. Initially, the volumes of the two compartments are equal, but the pressure are 3P naught and P naught respectively. When this wall is allowed to move, the final pressure in the two compartments become equal. The final pressure is. You understood the scenario? We have, let's say, this container. So it had a partition. Initially the volumes of the two compartments are equal. So let's say this is represented in this way. This is container 1, this is compartment 1, this is compartment 2. Initially the volumes are same. Let's say this is V0, here also it is V0, but the pressure was, it was 3P0 and it was P0. This is the initial configuration. Now this partition has been removed, so there is no partition here. So there will be nothing like compartment 1 and compartment 2. The final pressure has in the two compartments become equal. So let's say this is PF. Here also you will get the pressure PF, but the volume will change. Okay. Let's say the volume is V1 for the first compartment, second compartment is, okay, this wall is not removed, the wall is there, but the wall is movable. We do not know about the volume. It is given that the pressure is same. What is the final pressure? Look, if you consider compartment 1, in this case box is separated by movable wall and you see there is no heat coming out. So we can consider that the process is adiabatic expansion. Initially PV to the power gamma is equals to constant. So 3P0, this is the initial pressure, into V to the power gamma. So V naught to the power gamma is equals to, what is the final pressure? It is PF. Final volume V1. From it we can calculate V1. You see the total volume is 2 V naught, right? Initially the volume of the compartments were equal, total volume was 2 V naught. Now the wall has just moved, but the total volume will remain same. V1 plus V2 should give us 2 V naught. So from V naught, V1 is equals to, you see, 3 P0 V0 to the power gamma divided by PF, V1 to the power gamma. So let's say we make it to the power 1 by, let's call it equation number 1. Now similarly, if you calculate for compartment 2, what you get using the same adiabatic equation? Initially the pressure was P naught, volume was V naught. To the power gamma. Finally pressure is PF, volume is V2 to the power gamma. So from here we can calculate V2 is equals to, you see, P naught V naught to the power gamma divided by PF to the power 1 upon gamma. Let's call it equation 2. Now since V0 to V0, the initial volume, okay, you can say since the total volume of the initial and final configurations are same, we can write total volume of the initial configuration V0 plus V0, total volume for the final configuration is V1 plus V2, or 2 V0 is equals to V1 plus V2, you can say 3 V0 to the power gamma by Pf to the power 1 by gamma plus V0 to the power gamma by Pf to the power 1 by gamma. And from here, what you can write? Pf to the power 1 by gamma, if I take common and take it to this, what you are left with 3 V0. You see V0 to the power gamma into 1 by gamma, so V0. V0 is cancelling. From here also, if you take V0 is cancelling. You can write a line here. This is 3 V0 to the power 1 by gamma plus V0 to the power 1 by gamma into V0 divided by Pf to the power 1 by gamma. So Pf to the power 1 by gamma is equals to 3 P0 to the power 1 by gamma plus P0 to the power 1 by gamma divided by 2. And from it we can write Pf is equals to, you see, P0 to the power 1 by gamma into gamma. So P0 times 1 plus 3 to the power 1 by gamma to the power gamma divided by 2 to the power gamma. So this is the final pressure, and that is matching with option C. Is it clear, guys? Tell me. Calculation is little bit lengthy, but it is very easy. Let me know once it is done so that we can move forward to the next problem. Okay, let's try to solve this problem. For an ideal gas, the molar heat capacity varies as C is equals to Cv plus 3a square. What will be the equation of state for the process in the variable of T and V, where A is a constant, C is the heat capacity at constant volume? Molar heat capacity varies as C is Cv, so it is variation of C. Actually, this is Cp. Okay, so here Cp is C. Can you imagine? Molar heat capacity, so 1 mole is talking about 1 mole, then equals to 1 you can take. What will be the equation of state for the process? Can you do it? You can use the first law of thermodynamics and you can do it. You start with first law of thermodynamics. Look, although sometimes we are writing it in terms of differential, it is also writing, it is also equivalent to Q is equals to U plus W. Okay. dq is equals to n Cp dt. So here C is Cp, du is equals to n Cv dt, n is 1, so Cv dt, dw is equals to P dV. Now the variation of this C is given to you as Cv plus Ca T square Cv dt plus Pdv. Now can you not calculate? I have just done 25% of the solution. Now it's your turn to do the remaining. Acha, dt is dropped somehow. Cv dt will be cancelled from both sides. Tell me the answer, guys. P is equals to RT by V. One T is cancelled from both sides. So 3A times T dt is equals to R times dV upon V. Now we are in a position to take the integration on both sides. 3A T square by 2 R times, this is ln V, some constant will also come, let's say ln A. ln A is a constant, okay? We can take minus plus as per our convenience. So this is 3A by 2R E square equals to ln V by A. So to write it in this form of ln V by A, we have taken a minus sign. Constant, we can take anything as per our convenience. So V is equals to A, which is a constant, e to the power 3A by 2R times T square, and that means V e to the power minus 3A by 2R E square to constant. Na? and that is matching with option C. Tell me if there is any question, confusion, you can let me know. Is it done? Quick guys, hurry up. Okay, take this problem as homework. There's similar problem. If the equation of state for a gas with internal energy U is PV is equals to U by 3, then the equation for an adiabatic process is. So take this problem as homework. So you can try this by yourself and you can send the solution in the WhatsApp group. Okay. If not solved, then I will provide the solution. And the solution is generally uploaded in the course folder in the homework problem solution section. Okay. So this one you will do at home. Let's go to the next problem. The total energy E of an ideal non-relativistic Fermi gas in 3 dimension is given by this, wherein N is the number of particles, V is the volume of the gas, then what is the value of PV by E? Actually, this question is not part of first law of theory. It also requires the knowledge of second law. Okay, let me just provide you the solution. E is proportional to n to the power 5 by 9 divided by v to the power 2 by 3. So we can remove this proportionality sign by multiplying with a proportionality constant k in this way. Now, from the first law of thermodynamics, you know, energy, so generally we write it in terms of U, but here it is given E. So dE is du, you can say dq minus dw, dq minus pdv. Now, from the second law of thermodynamics, we will see dq has the expression of TdS. Okay, so dq is equals to TdS and therefore you see P, if you want to write it, dE is equals to TdS minus PdV. From this expression, if you want to write P, you see E is not a function of only one variable, it is a function of two variables S and V. So P we can write minus, we cannot write D, we will write del E divided by del V. If I write del E by del V, then you will get minus P. So minus, a minus symbol has been used. And if you make this S to be constant, at constant S, and actually there is another term here, mu dN. Mu is the chemical potential. So if you make S and N both constant, so change in S, ds is 0, change in N, dN is 0. So that is how the formula P is equals to minus del E by del V at constant S, constant N. If you calculate this, what value you get? Derivative with respect to V. So minus 2/3 K n to the power 5 by 9 will be treated as constant, V to the power minus 2/3. So minus minus plus 2/3, V to the power minus 2/3 minus 1 minus 5/3. What you are getting? You have to calculate PV by E, right? So is P is equals to 2 K n to the power 5 by 9 by V to the power 2 by 3. If I take okay, 2V if I write, then what you are left with? Divide into K n to the power 5 by 9 and V to the power 2 by 3 is coming down. Can you write it in this way? What is this? This is E. And this 3, let's say keeping it here. So P is equals to 2V by 3 and this is what? E, and hence P, acha, how can it be? It is V to the power minus 1, right? So this V is coming down. Now I think it is okay. PB by E is equals to 2 by 3. So that is 0.667 and C. Okay, got it. Let's check out this solution. As you proceed in this course, these things will be very much easy for you. But if you are learning it for the first time, it may appear to be little bit bitter, but it will get better with time. आगे बढ़ा जाए दोस्तों, can we move forward? One last topic is left, that is quite theoretical topic, reversible and irreversible process. What is the basic difference between these two? Any idea, guys? What is reversible process and irreversible process? When the process is taken infinitely slowly, then that process is reversible. You can reverse the process, and the whatever changes you have during the process will be reversed. For irreversible process, it is not possible. So I have a quick go through of this topic: reversible and irreversible process. The reversible process is one which can be reversed in such a way that all changes taking place in the direct process are exactly repeated in the opposite order and sense. No changes are left in any of the bodies taking part in the process or in the surrounding. Now there must be there are two conditions which must be satisfied to call a process to be a reversible process. The first criteria is the process must be quasi-static. What is the meaning of quasi-static? If the process is performed in such a way that at any instant during the process the system is very nearly in the thermodynamic equilibrium, then we call it quasi-static process. A quasi-static process is an idealized process in which all changes takes place infinitely slowly. Second criteria which must be held is the process must be non-dissipative. It means dissipative forces such as frictions, resistance, hysteresis, etc. must not be present, or it should be, these processes should be completely absent. Those forces should be completely absent. Now in this tabular form we have tried to represent the difference between reversible process and irreversible process. Reversible process is carried out infinitely slowly. Irreversible process is carried out rapidly. At any stage the equilibrium is not disturbed, it is maintained. In the irreversible process, equilibrium may exist only after the completion of the process. During each process you cannot expect the equilibrium to be held. Third, it takes infinite time for the completion because it is infinitely slowly process. For in the irreversible process it takes a very small time, a finite time for completion. Here in the reversible process it is quite obvious that the work obtained in this process will be the maximum. Here in the irreversible process it is not maximum. If I talk about the examples, irreversible process examples include isothermal expansion of gas, adiabatic processes, diffusion of a gas, transfer of heat from a hot body to a cold. These are all the natural process which we see in our day-to-day life. Or in general, almost all physical processes are irreversible in nature. Free expansion of perfect gas, heat transfer by radiation, electrical heating. For reversible, it is ideal reversible process is not possible. It is like time travel. So, but we can approximate almost reversible, we can say isothermal quasi-static expansion of a gas. So if you expand a gas infinitely slowly, then we can consider it to be an isothermal process, but ideally it is not perfect reversible process exist. Very slow expansion or contraction of a spring that can be approximated to a reversible process, but that is not an actual reversible process, because in real life you will be having different kind of factors which can influence and you will not get back exactly the previous state. Okay. So with this we have completed first law of thermodynamics. In the next lecture we'll be completing the second law of thermodynamics. Then after that we'll go for entropy, Carnot's heat engine and all, refrigerator and all, and it will be completed in less time, don't worry. And as you can see, you must be enjoying this thermodynamics topics. These topics are very much easy topic and easy for answering questions in the CSIR-NET exam. Okay guys, so we are stopping here today. Thank you very much for joining the session. Have a great day. Bye bye, take care. And whenever you watch the video, you hit the like button every time. Okay, I don't say it, but it's your duty. If you like the stream, you should like it. Chalo, bye.